Here's another video to the lecture Intro PDE. In this video we present the section 4.7. In the section 4.7 we determine the heat kernel of S1. So what means S1? S1 is the circle. It's the circle, and we identify the circle with the quotient space of R divided by Z. So the Laplacian is just the second derivative along R, so it's just d by dx square. This is the Laplacian. So by our strategy, in the last section, we introduced the relation between spectral theory of the Laplacian and the heat kernel. So, and this we now want to apply to this situation, because in this situation it's quite easy to decompose a function into an eigenfunction of the Laplacian. Okay, let's first determine the eigenfunctions of the minus Laplacian. Since minus Laplacian is a positive operator, we always take this minus in front of the Laplacian. Now clearly exponential of 2 pi I kx are eigenfunctions of the Laplacian. So if we calculate the second derivative, square of exponential 2 pi I kx on the real line, then this of course gives 2 pi I k square times exponential 2 pi I k x, and this is of course minus 4 pi square k square exponential of 2 pi I k x. So minus this operator has the eigenvalues 4 pi square k square. Now this eigenspaces in L2, so if we use L2 of R divided by Z, this means we just integrate from 0 to 1 for all these functions. Then we know that the integral of exponential from 2 pi I kx times exponential 2 pi I k prime x dx from 0 to 1. So in this we take this. We can take here over an arbitrary interval of length 1. Okay, we choose this interval. Then this is of course integral from 0 to 1 exponential of 2 pi I. Now, what is this? Chi prime. Okay, this is chi prime. The complex conjugate, here we just have to take the complex conjugate inside the exponential, and this is minus. So we have 2 pi I times x times k minus k prime dx. And this is clearly, this is what comes out. This is 0 if k minus k prime is not 0, and 1 if k minus k prime is 0. So we see that this is indeed an orthogonal system. Also in this situation it's if this is non-zero, then the antiderivative is just divided by 2 pi I k minus k prime, but this function is periodic. So if we evaluate exponential here to calculate this, for k minus k prime not equal to 0, this is the this is equal to exponential from 2 pi I x k minus k prime, and now 2 pi I k minus k prime, evaluated from 0 to 1, and this is 0. Yeah, so we see this, and for 1, if this is 0, this is clearly the function 1, so this is also clear. So we indeed see this is an orthogonal system. Now we know, yeah, that by the theorem of Stone and Weierstrass, polynomials, the polynomials with respect to so the algebra, the polynomials with respect to x going over exponent e to the power 2 pi I x, and x going over to exponential minus complex conjugate. Yeah. They form a dense subalgebra of the continuous functions on R modulo Z, on the periodic continuous functions. This is a compact space, and so we may apply this theorem of Stone and Weierstrass, and then this shows that this is indeed a dense algebra, subalgebra. So this, since the continuous functions, since the continuous functions, since C of R mod Z is dense in L2 of R mod Z, we obtain that the orthogonal complement, or let's say it differently, that we first obtain that this subalgebra is also dense, is also dense in L2 of R mod Z. So the orthogonal complement, so the orthogonal complement is trivial. Yeah, and this shows, therefore, this functions I k x with k labeled by integers is an orthogonal basis of L2 of this space here. And this is very nice, yes. So this means we have H is equal to the sum K over K in Z, AK times this functions, exponentials 2 pi I kx, with, now with AK, it's just the integral, of exponential 2 pi I k minus a complex conjugate dy, 0 to 1. So we have, this means this gives for any h in L2 of R set a decomposition into eigenfunctions of minus d by dx square of the Laplacian, or of the negative of the Laplacian. So this means, therefore all h in L2 of R modulo Z, we can now write down the solution, the function, the following function, u of xt. This is sum n in the integers. So we should take n in the integers, exponential. Now we should take the eigenvalues minus 4 pi square kt times a k times exponential from 2 pi I k x. Solves this function. With ak is equal to this integral from 0 to 1 minus 2 pi I k y h y dy solves the initial value problem. U dot minus d by dx square of u is equal to 0, and u of x0 is equal to h of x. So we have this initial value problem. Now let's write this. Now, because now we can derive from this the formula for the heat equation. So u of xt. Now write this in one formula. So we have this sum k and z, and we have the integral from 0. Or maybe we write more general, integral over R mod z. And then we have exponential minus 4 pi square k squared t. Sorry, here is missing a k square. The eigenvalue was k square. So k squared t, then plus 2 pi I x minus 2 pi I y times h of y dy. So this is the formula. Now if this converges, and clearly this converges, because here, sorry, he is missing, of course, k kx minus 2 pi I ky. And this here, So this solves is the solution. But this we may also write as integral over R z times, and here now should be the heat kernel, x, y, t, h of y, dy. Yeah, this we can take as a definition of the heat kernel. Yeah. Okay. So this gives that the heat kernel of the circle of x, y, t is just the sum over the integers exponential minus 4 pi square k square t plus 2 pi I k times x minus y. Yeah, so this is in, yeah, if we can combine this 2 pi I k times x minus y. Okay, so we indeed have this formula for the heat kernel. Now we may write this also in terms of the theta function. Yeah, this is the same as the theta function of x minus y 4 pi I t. Yeah, where the theta function of x and tau, usually the second argument is called tau, this is defined as k in z exponential 2 pi I k x plus pi I k squared tau. Yeah, and this is defined for positive imaginary part. Yeah, for imaginary part of tau should be positive. Yeah, because then this is negative here, then when for if the imaginary part of tau is positive, then the real part of pi I tau is negative. So this exponentially decreases here, and so this clearly converges. Yeah. So on this domain, this converges. The sum converges to a holomorphic function with respect to x and tau. Okay, this theta function is characterized. You can find in textbooks this theta function, and it's characterized by 3 properties. Yeah, so it's periodic by period 1, and it's quasi-periodic in direction of tau. Yeah, where we get this phase, and it has roots at these places. So this property, the first property, is clear. Yeah, since exponential of 2 pi I k x plus 1 is of course exponentials 2 pi I k x times exponentials 2 pi I, and this is of course exponential 2 pi I k x. So since these functions are periodic with period 1, yeah, this first property is clear. Now we calculate the second property. Yeah, we calculate the second property. Okay, here we just insert the definition of this formula, and now we write this in this form. k plus 1 square. If we multiply this, then we get k square plus 2k, yeah, plus 1. K square plus 2k tau, 2 pi I k tau. Then we get this term here. Yeah, and here we subtract the term which we get by the 1. So this term indeed gives this term here and the k square, and if we subtract this, then we get this. Okay, and now we may write this in this form. Yeah, here clearly this is the same. If we, this plus this, here, minus this term, this is clearly exponential 2 pi I kx. So now we may relabel k plus 1, yeah, because k mapping to k plus 1 is clearly a bijective map from set to set. So if we have this sum here, yeah, and clearly the series converges absolutely. So we in this domain, so we may relabel. Yeah, now we call k plus 1 k prime, and then take the sum over k prime, and then we see we get again theta of x and tau with this times exponential of this. So this shows the second property. Yeah, this shows here this property, and now we want to calculate this function. Yeah, and here exponential from 2 pi I k times 1/2. This is of course exponential from pi I k. Yeah, and this is minus 1 to the power of k. So there we get this minus 1 to the power of k. Yeah, and all other terms we just have so here the k we have, then we have 2 pi I is, but this is just 1. Yeah, 2 pi I is 1, so this term we don't get. No, sorry, we are here. So we have this term here, and now plus tau, the terms with the tau halves here. This is this. So maybe I write it theta of 1/2 plus tau half tau. This is by definition sum over k in set exponential of pi I k, 2 pi I k times 1/2 plus tau half, and then we have pi I k square tau plus pi I k square tau. Yeah, this is just the definition here. This first factor gives minus 1 over minus 1 to the power of k. This is this first factor. Yeah, this we calculated here. Now 2 pi I k times tau half is pi I k times tau. Here, if we multiply this out, then we get an k square plus k plus 1/4. And the plus k gives us exactly this term here. Yeah, this term here. The k square we already have, and the 1/4 we subtract again. So we have this formula. Now we put this factor here. We put this out because this doesn't depend on k, so we can put this out of this sum, and then we have this sum, and now we label also if k plus 1 runs through, sorry, k plus 1/2 in Z, yeah, this is of course equivalent that k, also k plus 1 in Z, that k plus, sorry, 1/2, also the set, maybe I write it differently to make it clear. So k plus 1/2, this set, k runs through Z. This is of course the same as k plus 1/2, k in N0. And now what we have, what is missing, here we start with 1/2. Okay, what is missing is k plus 1/2 minus k in N0. Yeah, but for minus k, now we have also the difference, yeah, of minus k plus 1/2 is of course the same as k plus 1/2 plus 2k. Yeah, so we have plus 2k and okay, so but the square, yeah, this is this differs, yeah, minus k plus 1/2, no, square, this is of course the same as k minus 1/2 square, and this is of course the same k plus 1 k minus 1 k minus 1 plus 1/2 square. So we see for the negatives we have the k is shifted by 1, so we get a negative sign by this factor. Yeah, so the negatives we can also, since the square doesn't change if we have the negatives. Yeah, so we get once this sum here, but for the negatives we get the negative. So we get this sum once and we have to subtract it. So altogether we get 0. So this shows that this function really vanishes. Okay, so yeah, our function indeed has this property, so it's really this theta function. And now, yeah, here in this exercise I described another method how to derive this formula for the heat kernel of S1. So this is already the end of the section. So what we have done in this section, yeah, we introduced the circle, described it as the quotient space of the real line divided by the integers, and then with the Laplacian. And on this space we can easily determine, decompose any function in the Banach space L2, in the Hilbert space, sorry, of L2 functions into a sum of eigenfunctions of the Laplacian. This is also the Fourier transform for this space. Yeah, and then we applied our method and derived the formula for the heat kernel and showed that the heat kernel is indeed given by the theta function. Yeah, so this is a nice formula for the heat kernel on the circle. So thank you.